Just as the beard grows longer and longer each week, so we move further and further into understanding the research literature so that we can critically appraise it and we can develop our own ideas about the quality of evidence. And that's the whole point of this class. Now, the truth of the matter is most of you, when you read articles, and this is certainly true for me for a number of years, is I would just skip over the results section. I would read the introduction. I might read some of what the data sources were, and then I would jump quickly to the discussion section and skip right over the whole results section where the meat of the research is. And the point of last week was to introduce some of the concepts, and the week before that to introduce some of the concepts from both qualitative and quantitative points of view to begin to help us be able to digest the density of that information presented in the results section. And today we're going to go into depth about the analytic procedures around both inferential statistics, and that's where we're going to start, and then we're going to finish up with another discussion of qualitative coding and some of the sausage making processes of qualitative research. So by the end of this week we will have completed almost everything in a paper with the exception of wrapping it up in the discussion section and then a few other elements. And so we are well on our way through the class, and the idea behind this process that we're going through is that for the worksheet questionnaire, for the worksheet assignment, you should be able to then go through an article, break it into its specific components, critically evaluate each of those components, and then resynthesize an interpretation of that article. But in order to do that, you have to understand how the sausage, that's the results section, gets made, and that's what today's lecture is about. Last week we talked about the p-value, and it's a very important concept, but it's also a hard concept to wrap your head around. And the basic problem with understanding a p-value is it requires us to flip what we think of as our hypothesis into a null hypothesis. So our hypothesis might be something like giving people supported housing as opposed to letting them be homeless will reduce the rates of emergency room use. So the idea is that supported housing, as opposed to being homeless, means that people are going to go to the emergency room less and less and less, and that's a good thing, and that's what we want. We're implicitly saying there that there is a difference in the mean number of emergency room uses in the supportive housing group than in the usual care group, that there'll be a lower number of emergency room admissions in the supported housing group than in the control group. But when we do statistical testing, when we do inferential statistics using p-values, we flip that idea and we say there is no difference between these groups. And we're going to have to find a difference that's not explained by random chance in order for us to believe that that difference is caused by supportive housing as opposed to just random chance. Now, we have a picture of random chance, and traditionally, and in most of the tests, and certainly 2 of the 3 tests we're going to talk about today, that's a normal distribution. That's how we think of randomness. And so today, we're going to talk about the statistical tests that use that concept of the p-value and put it into operation. We're going to talk about 4 different forms of statistical tests today. They're all tests of association to see whether the independent variable is associated with the dependent variable. They're all going to rely upon this concept of the p-value and the null hypothesis to tell us whether there is a difference between group A and group B on whatever the outcome is that we're measuring. The 4 are correlations, t-tests, chi-squared tests, and multiple regression. Multiple regression is going to be a slightly more complicated one, but it's also probably the one that is in most of the papers you're going to look at, and we'll try to get a simple idea of what's going on in that at the end of this section on inferential statistics. The thing about these different forms of tests is that they each rely on a different set of variables, kind of variables. That's why we went through this idea of mapping on the nominal, ordinal, interval, and ratio to dichotomous, count, and continuous, because dichotomous, count, and continuous variables are all treated a little bit differently in terms of the statistical tests that are used. For example, The chi-squared test, which we're going to start with, requires two dichotomous variables. So you can use two nominal variables, you can use a nominal variable and an ordinal variable. Anything that can be fit into that dichotomous camp is appropriate for a chi-squared test. But what if we have an example like we just said, where we're counting the number, where we have an interval level measurement, like the number of hospitalizations, and we have a dichotomous variable, supported housing or usual care. So the usual care or supported housing is a dichotomous yes, no, 1, 0 variable over here. There's a count variable where we start with 0 and go up to however many hospitalizations over the course of time. And so in order to test for that, we'd want to, there's a number of ways you could test for that. The one we're going to talk about is a t-test, where we would say, are the mean number of hospitalizations in one group, in one dichotomous category, different than the mean number of hospitalizations in the second dichotomous category. So on one hand, we have a count or continuous variable. On the other hand, we have a dichotomous variable. If we have two continuous variables or count variables, we can use a correlation to look at the association. How strongly are they related to one another? And then multiple regression borrows on a number of these concepts and can use a variety of different forms. And we'll talk about how to interpret multiple regression a little bit. Chi-squared tests use two dichotomous variables or ordinal variables. So you might be asking a question about the association between male and female and stated health status, whether it's good, fair, or poor. This would be a perfect use of a chi-squared test because it tests whether these two variables are independent of one another or are associated with one another. And it does it by doing a simple breakdown. It says, okay, if they're related, if they're not related, they look like this. And there's a formula for doing that, and we're not going to talk about the formula, but trust me, there is an actual formula where you could say if there's no relationship between the variables and we know what the margins are, we can then calculate what the expected values in each of these cells are, and then we see how different what we actually found is from the cells. Now, as with all statistical tests, our null hypothesis is that there is no difference between what we expect to find based on the assumption of independence between the variables, meaning the variables aren't related, and what we actually found when we went out and collected the data and compiled this 2-by-2 table. So if there's no difference, that p-value, which would be above 0.05, if we set the alpha level at 0.05, so it might be 0.1 or 0.2 or 0.8 or 1, right? So anything above 0.05, 5% of that 5% cutoff, we're going to say that that difference between what we expected to find with independence, with the assumption of independence, and what we actually found with the data that we observed are the same. That the differences there are just random noise differences, and they're not meaningful differences. But if the differences are going to be found less than 5% of the time, if that level of difference between the observed and the expected is so large that random chance isn't a good explanation, then we're going to assume that these variables are associated with one another. Let's look at an example of a chi-squared test. In the case of a chi-square, you have two binary or ordinal variables that we're going to ask the question whether there is a relationship between those two variables or whether there is no relationship. And of course, our null hypothesis is that there is no relationship. In this example, we have depression, whether somebody is depressed, has a depressed diagnosis or no depressed diagnosis, and whether they are male or female. So the question is there a relationship between gender and depression diagnoses? In the case of the cells here, you can see that there are 23 females with no depression diagnosis and 28 with a depression diagnosis. So there are 5 more females that have depression diagnosis than don't. Males have the opposite. There are 29 males with no depression diagnosis and 20 with. So there are 9 more males without a depression diagnosis. Now, the question is this something that we'll find by just random chance alone? Is that level of difference? Since, again, if we flipped a coin, we're not going to get 50-50 most of the time. We're going to get something in the 45 to 55 or 65 to 35 range. In the case here, we have a difference between males and females with respect to depression diagnosis, but we don't know whether that's large enough that random chance can be excluded as the possibility. So in the case of a chi-square test, what we do is we calculate an expected value based on the assumption of independence between the variables, which just means that the variables aren't related. We then take two of them. In this case, we'll take 28 and 24.5. We'll subtract the difference from the observed 28 and the expected 24.5. We'll get a value, we'll sum it up, we'll square it, that's the chi-squared part, and when we add up all the differences, we convert that to a chi-squared value. Here's a picture of the chi-squared distribution, the only non-normal distribution that we're going to deal with in this class, and you can see that the chi-squared, the red line there, represents the critical value, and our chi-squared value for our example of 1.99 falls to the left of the chi-squared value, which means the p-value is greater than 0.05. In fact, it's 0.16. So 16% of the time, we are going to get a value, a chi-squared value of 1.99 or larger, and that suggests that randomness is a good explanation for the value that we got. So if we review the null hypothesis, which is that there is no difference between men and women's depression diagnosis, we're going to accept the null hypothesis because our p-value is greater than 0.05. It's 0.16. The alternative hypothesis that there is a difference between men and women's depression diagnosis is going to be rejected because we have a p-value, once again, that is larger than 0.05. Interestingly, I simulated the data. I constructed this data, and so I know whether there is truly a difference or whether it's just random chance. And in fact, there was an actual difference between the probabilities of being diagnosed depressed or not depressed, given male or female. But we were not able, given the sample size and given the magnitude of difference, to detect the difference between what we found and what random chance suggests is a likelihood occurrence. And I think there's an important message here. It's that just because a p-value does not exceed 0.05 or go below 0.05 does not mean that there isn't actually a difference. It just means we do not have evidence that there's a difference that's different from what random chance would imply. And so I think it's important to distinguish between reality, real differences, and what the hypothesis test is actually testing, which is just the question of whether randomness is a good explanation for a difference of the magnitude that was observed. And in this case, randomness is a good explanation, and so we will accept the null hypothesis.